Hey everybody, Jacob Klein again. This time around we're going to talk about moisture. Some of the two basic things where moisture really affects us in flying helicopters is the weather and air density. So, you've been familiarized with weather and you probably know by now that the cause of all weather is the uneven heating of the Earth's surface. But one thing you probably haven't been familiarized with yet is moisture is the true culprit for what stores and releases energies in storms. Releases energy in storms. This is because of latent heat. Keep that term in your mind, and we're going to backtrack one step to evaporation and condensation. So evaporation is, you probably already understand this, but evaporation is when liquid water changes into a vapor. And vice versa, condensation is when it goes back into a liquid. There's also sublimation. This is where it goes from the ice state directly to the vapor, or the vapor directly to ice, like frost that forms on your car at night. That's sublimation. Latent heat then. We'll get back to latent heat now that you are familiarized with evaporation and condensation. Latent heat is a term that refers to what happens to the heat that turned that liquid water into vapor. The way I like to think of this is the heat. So in physics we know that heat is just a measure of kinetic energy. You think about that, a measure of kinetic energy. Kinetic energy is movement. So heat is just a measure of how fast something's molecules are moving. This also can help explain why burns do so much damage to your skin. It basically transfers so much kinetic energy to your cells, your skin, that it scrambles it like an egg, and that's why it's so damaging. So back to latent heat, this kinetic energy that is used up to change water into vapor, it takes a lot of heat to move this water from liquid to vapor. That heat doesn't just disappear. What happens is it turns into kind of a what do you call this? The motion is what keeps the water vapor and the molecules spread apart so that they are opposing each other. It's like opposing magnets. It's kind of hard to see, but I colored it kind of just so you can see a little better from that range. But solid, liquid, and gas, these are all three water molecules. And the liquid, once it takes a lot of energy to move it to the gas form, where the molecules repel each other. That's the better word for it. Where the molecules repel each other. That's kind of where the heat goes, is into the kinetic energy that maintains this separation of molecules. That's what I was getting at. Man, kept choking on that one. Alright, so the other part with the weather and this latent heat that's stored in there, Hurricane Sandy that just happened, you kept hearing them talk about all this energy that this storm was gathering. What was happening is this water off the ocean, warm water and warm air on the ocean was evaporating just tons and tons of moisture, and it was building and building and building. And all of that moisture had latent heat. All that warm, wet air had latent heat. Now, the more of that you build, the more energy the storm has in potential-wise. So once it hits landfall and this moisture starts to condense again and the heat is released, what happens when you heat something is it expands. Well, you heat this, you recondense the water, you release all these tons and tons of kinetic energy back into the atmosphere, and it is just like putting gas in your car. I mean, it just keeps fueling itself. So that's kind of the effect of moisture in weather as a broad overview. The next basic thing that I wanted to touch on was the adiabatic lapse rate. So the adiabatic lapse rate refers to the rate that a given air mass cools as you get higher in altitude. We use an average rate, which is 2 degrees per 1,000 feet. 2 degrees per 1,000 feet, 2 degrees per 1,000 feet. Every 1,000 feet you go up, you will lose 2 degrees in the same column of air, vertical column. That being said, there's a saturated and an unsaturated. Saturated air, because it takes so much energy to cool or to heat it because it has moisture, only cools between 1.1 degree per 1,000 feet and 2.9 degrees per 1,000 feet, just depending on how saturated the air is. Unsaturated, which is dry air, cools at a rate of 3.3 degrees Celsius per 1,000 feet. That gives us 2 in the Pacific Northwest as a nice, safe generic lapse rate for us to use for a performance calculation in the cockpit. It's never going to be, you're never going to go wrong using 2 degrees around here. That's a pretty generous one. What else? So clouds. Clouds are a visible aggregate of tiny water droplets or ice crystals. So it can be either or, tiny water droplets or ice crystals, suspended in the air. Don't let this confuse and say that clouds are vapor. Clouds are very much not vapor. Vapor is invisible by definition. These water droplets that clouds are made up of actually have mass of water, and they're just very, very small. That's the only difference. That's why they can also be ice crystals. There's 3 basic groups for clouds. There's cirrus, which are above 20,000 feet, and they're almost always going to be ice, made up of ice. There's a few exceptions. A towering cumulonimbus can push warm air up far enough to where you'll actually have water vapor at the cirrus level. The second level, which is altos, which is mid-level, between 6,500 feet and the 20,000 level are altos. And those are mostly formed of water droplets, but there's still quite a bit of that can be snow or ice crystals. The low-level clouds below 6,500 feet are almost always water vapor. And the few exceptions are, if it snows outside, well, you've got water. That's ice. Alright, so air density. For air density, the one thing we have to understand is when water is in its vapor form, it weighs less than air. It has less mass. And that right there should tell you that it's going to hurt your performance. The humidity, as it increases, the air mass, the given density of that air mass decreases. So as humidity increases, the density of a given air mass decreases. Hot air can hold more water vapor than cold air. There's a couple of reasons this is important to us, but the main one is performance. And like I said before, because that hot air holds more moisture than cold air, if you have, say, a 30 degrees Celsius parcel of air and it's at 10% relative humidity, it has more moisture in it than a 20 degrees Celsius parcel of air at the same 10% relative humidity. And that's why it's called relative humidity. It's relative to the temperature. The temperature determines how much moisture that air can hold at a given temperature. Or, I'm sorry, did I say that right? Yeah, the temperature determines how much moisture that parcel of air can hold. So 10% at 30 degrees Celsius holds more moisture than 20 degrees Celsius 10% can hold. Therefore, the higher the temperature, that's why we have that density altitude calculation. And you can see just how much each degree counts against you in density altitude, and that's why right there. We don't have any charts that specifically deal with moisture in air density and directly relating to that, but never underestimate the effect that is going to have on the performance of your flight. That could be the straw that broke your camel's back, so to speak, if that's your only leeway is, oh, well, our density altitude says we're okay. Well, your temperature is, 30 degrees, so don't cut it that close. Always give yourself a little extra room for high temperature in your performance calculations. That was really rough, but the review, basically we talked about evaporation, condensation, and sublimation, and about latent heat and the energy that it stores, the unsensible energy that it stores. We also talked about density altitude and the performance, how it affects our performance calculations, and how about air density decreases with moisture, and warm air can hold more moisture than cold air. Those are a few of the important things that you should keep in your back pocket. We definitely want you to know the answer to what's the average lapse rate we can use in the cockpit for performance calculations. And you remember, that's 2 degrees per 1,000 feet. Good. If you're in the desert during 0% humidity conditions, is that going to change the number that you use in your head? If so, why? And what's the other number? The why is because there is no humidity, and you could just use 3 degrees if you know that there's 0 degrees humidity anywhere in the area or in that whole day, and that's going to give you a little bit extra that you can count on to be there. So the last thing is take 2 different air masses with the same relative humidity, one warm and one cold, which has more moisture. And the answer is the warm air. Right. That's all I have for this one on moisture. I hope you guys enjoyed it, or maybe at least picked up something new, and we'll see you next time.